Okay, we'll start today's lecture with this, with the continuation of what we began in the last class, what we started in the last class. We are actually discussing about groundwater contamination, and there in fact, I have discussed about the characteristics of groundwater sources, the characteristics of groundwater sources, or that we known as aquifer, that we know as aquifers. Having said that, I have also discussed about porosity, and I have explained you, the porosity would mean that the total, say the void volume divided by the total volume, isn't it? So this would, if you just try to understand little bit about this, there are another important thing is related to porosity is this effective yield. The concept of effective yield is like this. I mean, you say, even if in many cases, if you see, it's like, suppose you have weighted your clothes, how so well you rinse it, I mean, you just turn it and all that, there would be a certain quantity of water that would be essentially coming out. Not all the water can come out, isn't it? So that, when it cannot come out, so it takes about the specific yield. Even if the water content may be say 20% or 30% of the volume, but only the available water that can be drained out would be about 20% or so. So you find a specific yield. That is about a structure depending on a particular kind of structure. That is what is, in addition to porosity, we will also have another parameter which is known as effective yield. The effective yield suggests the water available for transportation out of the aquifer, suggests the water available for transportation out of the aquifer. So it's not necessarily always, it's always, as you can observe, always effective yield would be less than porosity. Effective yield would be less than porosity. The same example can also be given, the example that I have given for soil, for any other say geologic structures, any other kind of geological structures. You can think of, even if the water may be contained water may be 30%, the whatever that is available for transportation may be only 20%. So 20% of the volume. So here in such cases, so you can see that the effective yield or the porosity would be always, and the porosity would be always more than the effective yield, or effective would be less than the porosity. So in such cases like this, let us just have a brief idea about the values, representative values. Values for soil and other geologic materials or other natural materials. As you can write this, representative values of, say, the material is this is porosity, and this is specific yield. Percent. If you just say this clay, as will have high porosity, but specific yield is very less. Specific yield is very low. The soil, the water in the soil would not be available for transportation. So here in such cases, we can find out that in other cases like this, sand is 35%, 35 and 25. This is gravel and sand gravel and sand 25 and 22. Says sandstone is 15 and 15 and 8, and this one is just make a correction here. Gravel and sand would be, gravel and sand is 20, this one is not 22, is 16. Okay. So says gravel itself only would be, gravel itself would be is about 25 and 22. So this is by Lindsay. Lindsay et al., that is 1975. The significance of et al. Is there are few more in the group. So that name, if it is not necessarily to be mentioned, we generally say et al., Lindsay et al. In 1975. This is just to give you the specific yield of different water bearing formations, particularly the aquifer. So the aquifer, you can see this, what is understandable here is here it says that the clay can contain about of its volume 45% as water, whereas gravel, sandstone, sand itself can have about 35% of the void volume would be 35% of the total volume. That is signifies. So the void that would contain water, would be about 35% of 100% for sand. So it is the available water is 35, but only transportable water, the water that can be drained out, is only about 25%. Rest of the water would be locked into the structure itself. Okay, either in the form of vapor or in the form of water. Okay. So this is what is means by these two terms, porosity and specific yield. Another very important property, particularly related to this groundwater, is hydraulic gradient. The word this hydraulic gradient, hydraulic gradient is a very important aspect. Say in case if you just observe that there would be if you just can draw a scheme like this, here it is a groundwater, and you can see this is what is the groundwater flow taking place from one area to another. Say from one area to another, we can see this is the piezometric level. This is the piezometric level of water we are obtaining. This is in the structure. So here you can see this is a piezometric level. Here you get a piezometric level also here. So this is where the water is. This is the water being flown through the rock structure. So it is getting transported from the higher gradient side towards the lower gradient side. Okay. So as you can see this, as you can see here, so here as you can observe in this diagram itself, if you see this, if you just put this like this, and if you just make a difference in this, this is what is del H, the difference of head. Okay. What I am trying to say is the water flowing in this direction, water moving, we should not write flowing, water moving in the direction, water moving in the direction. So here we can see this, this is, as we observe here, water moving in this direction. And as you can see here, this particularly, there are two ways. One is, in many cases, say this one is known as, this one we generally call as del L. The del L in two ways, generally in a case of a very long aquifer, this would also be sometime known as del L. Okay. When the aquifer we are considering, we are discussing is a long one, then we can think of the values, the del H, this del L and del L dashed or whatever, in many cases we will say consider del L is equal to del L dashed. So this one would be almost same, would be considered same. So if it is a long, very long aquifer, we can consider that this del L by del H, this one is same. So here in such cases, the hydraulic gradient is the difference in hydraulic head divided say between say a hole A and hole B, difference in hydraulic head divided by the difference in difference or the distance between them, or the distance, say distance so you can see this as del H by del L. In many cases it can be del L, this is del H divided by del S dashed. We can, in most cases, when the aquifer is very long, when the aquifer is a very long aquifer, when the distance is this del L, when del L and del L dashed are very long, then we can consider this to be almost same, isn't it? So this is, but for almost all practical purposes, whenever if otherwise specified, if otherwise not specified, this would mean this distance. Remember this. If it is not otherwise mentioned, this is the exactly the distance that is should be covered as del L dashed. So we should consider in all practical purposes to make the correct judgment about the hydraulic gradient, del L dashed should be considered. Okay. Now, having said this, just let me explain you how we can generally find out the hydraulic gradient. This is about a two-hole case, which is a straight case, but in many cases it may not be so straight. Let me explain you like this. Say this part is clear. So far there is no problem in this. This is only an aquifer. We are trying to observe the flow direction. We are trying to observe the flow direction, and to observe the flow direction, what is done is two boreholes are driven at a distance. The boreholes, in the boreholes, the piezometric water head is calculated. It's nothing but when you strike the water level here and the water level here. These two differences, the difference in these two levels should essentially give you del H, isn't it? This should provide you del H. So having found out the del H, and if we know the distance between them, you can find out the hydraulic gradient. Now, it's essentially what is observed, the basic principle is that water from a high head would travel towards the water at low head, right? This is just as simple as that. But here else, we would try to see how this can be, how this is computed. Suppose, say various areas, suppose in a mine area or any other agricultural field or any other places, like for our practical purposes, we generally want to find out the hydraulic gradient. What is, say, the boreholes are like this. The boreholes are like this. The boreholes have been, say, made like this, is about this, and say we have made the boreholes quite regularly. Say, so you can see, if it is essentially, it has to be in the form of a grid. Essentially, it has to be in the form of a grid. Always, it is always has to be in the form of a grid. So let us compute this one as like this. Okay, what we see is the water level here. Say water head here is, say, 30 meter. Okay, we find that this water here is about 32 meter. Sorry, this one is 30 meter. This one is 28 meter. 28 meter. This one is also having a 28 meter. 28 meter we have computed, and this one is at a further distance from this, we just gone it as 27 meter. What is this? This is the water head. This is the water head. Remember this. This is a water head. How to compute the hydraulic gradient? How to compute the hydraulic gradient? Say, in most cases, one very simple thing here is, for this, one value of hydraulic gradient is like this. If you just observe this one, this is called an equipotential line. Equipotential line. It's known as the equipotential line, which is having a equal potential. The water head is same. Okay. So if it is in equipotential line, what we generally try to do is, from here we draw in the plot, in the table, we generally plot write a perpendicular on that. So here it becomes, also all, as you can see, we can conceptualize that this value is about 28 meter also. Here, this is because of the equipotential line. Okay, this equipotential line, from this we would find out, say, this is what is the head, the hydraulic gradient is hydraulic gradient, one value of hydraulic gradient. This is, say, hydraulic gradient 1. Let us keep that hydraulic gradient 1 as this. So we would say this is hydraulic gradient 1, and this one is, so we can find out the value, like, say, 28 minus 27 meter divided by this distance. Say, if we just put it like A, B, C, D. So we find out this as the distance. This distance is, if this distance is measured, we can find out the hydraulic gradient, isn't it? This is one value of hydraulic gradient that we are going to obtain. Any confusion? No confusion. So it's okay. Now here, suppose we have to incorporate this one also. We have to incorporate this one also. There are two ways to do this incorporation here. One is you just find out here. Just see this. One way of incorporating this to 30 meter here is this. What we do, try to follow this. This is what we try to do is, we generally draw a line, connect this, just merely connecting this. Okay, I think somewhat not straight line anyway. So what we try to do is, between 30 meter and 27 meter, say, among this, around these distances, say, we find 27 to 30 meter. So if you are, this is a 3 meter gap, let's say 3 meter difference in the head. If we just distribute this 3 meter head into along this line here, so you can find say this is where we are getting the 28, 30, 29, sorry 29, say this one is 20, no, 30 to 27, right. So 20, 30, 29, okay, 29 is here and then 28 here, okay. In such cases, what we observe is here, again we have to make a equipotential line from here. We can find this equipotential line like this. We connect, this one is the new equipotential line. This is the new equipotential line. This is 30, this is 30, 29, 28 here, apart from this. So we find that this is a new equipotential line. From this there, so we will find out that the distance 28 minus 27, 1 divided by this distance here, this d, would provide you the new hydraulic gradient. So the objective here is to, let me explain you further on this. Here if you just observe, due to, this can result due to different aspects, due to different reasons. This can result in due to different reasons. The different reasons should be, say, the different reasons may be, in case of like a certain particularly least resistance area working in this area. So you can have a widely distributed. Here you can say 28 meter we have found out here, but this 28 meter has to be further modified. In such cases, this one would be, we are going to find another equipotential line, and that has to be explained like this, and has to be found out this distance equipotential line, the equipotential line considering the 3 points, and the distance from the equipotential line, the perpendicular distance from that point to the equipotential line, and divided by the distance. Okay. So let me take you another example in this case. Generally, what we generally try to do is like this. Say there is an example like this. We have a plot . In cases when the plots are quite in a perpendicular fashion, it is much more easier. It is much more easier to find out the equipotential line, mostly in a generally done in a grid pattern. So you can always find out the values like this. Say here for the same case, say for here this one is say 32, this one is 31, this one is 31. This one is 31 and this one is 30. Okay. There are two ways to do. The procedure one is, you can extrapolate this. You can extrapolate this to, so almost the same distance at the 30th. So this is 32. And then you can connect this to, this is becomes the equipotential line here. And then from here you can find out the perpendicular and can find out the hydraulic gradient, isn't it? So you can find out here, say A, B, C, D, E, it is F. So you can find out is hydraulic gradient is 32, 30 minus 32 minus 30 divided by AF. This is one way. Another very straight way is, this. you can calculate this 31 meter here and can find this perpendicular, can find the perpendicular. So, it can be somewhat changed or say similar. In that case, f dashed, this af dashed, this is another is 31 minus 30 divided by af dashed. This would be, both of them would be quite same. They would be, if you say this is 1, this is 2, we generally find that hydraulic gradient 1 would be similar to hydraulic gradient 2. Now, question is, having said this, is there always an equipotential line? I mean, or is there an equipotential line which necessarily has to be straight line? It is not. It is not. But in such cases also, the approximation is, even if say even if it is the equipotential line may be like this, or it can be like this, or it can be like this as well.
Generally, it gives us somewhat closer.
Yeah, they lead to somewhat closer. So, you can see this equipotential line not necessarily has to be a straight line. It is not necessarily a straight line. So, here in such cases, we can find out the equipotential line at different points. Equipotential line we can find out at different points. Say here there is one equipotential, this is one hydraulic gradient that you can see here. There is, you can find another hydraulic gradient here. We can find another hydraulic gradient here. So, average of that would be the hydraulic gradient of the field. This is called the hydraulic gradient of the field. This is how we can compute the hydraulic gradient. But in necessary cases, generally we, for say, if say for 100 200 meters, when the number one, when the distance between the holes under consideration are large, the hydraulic gradient should be computed with a non-linear equipotential line. The non-linear equipotential line. All right. When it is start that with a non-linear equipotential line. In such cases, in a non-linear equipotential line, so this is distance, say for distances more than 500 meter from each boreholes. If the distance is for more than 500 meters, so we can find out that that this is a non-linear equipotential line. We have to find out the hydraulic gradient at all points, and from there we have to compute the average hydraulic gradient, and that would be used for the total field, total groundwater body. Or otherwise, when the distance is small, is small, say about 50 to 100 meter, small, say about 50 to 100 meter, say linear potential line, linear equipotential line is justified. So essentially it becomes an engineering decision. It becomes an engineering decision as to how to compute, but the method of computation remains the same. That is, the change in the water head divided by the distance. Most in all cases, it is the perpendicular distance that is under consideration. That has to be a perpendicular distance. So this is, this is one way. So a hydraulic gradient has to be found out, and a hydraulic gradient is a very important property that is required to be found out in almost all cases. Is particularly when you are working on this groundwater contamination. Another important thing that is, is the particularly the one that is the flow for flow. So this is groundwater flow. When you are discussing groundwater flow, essentially what you start with, we start with a basic, very simple presumption that the flow behaves in a fashion that can be represented by an equation known as Darcy's law. The flow can be Darcy's law. So this is the force, the Darcy's law. The flow can be characterized by an equation known as Darcy's law. The Darcy's law says is very simply, it is this the quantity, that is meter cube per hour, meter cube per minute flow. This is Q is the flow multiplied by K. This is this is as the hydraulic conductivity. Then dH by dL is the hydraulic conductivity. This is the conductivity coefficient K, and this one is A into del into A, area of cross section. Let me explain you this here. Even if if it is pictorially, if we just try to observe this, if we just pictorially try to observe it, suppose this is a groundwater. This is a groundwater block that can be represented like this. This is a groundwater block that can be represented like this. So here in such cases, this is the groundwater. This is the total cross section, one cross section of the groundwater, looking like this. And you can see here, this is where it is finally heading to. This is where it is finally heading to. Okay. See, this is the area A. This is the area A. This is the area A, cross sectional area. We are just considering a particular block, a particular cutout in the groundwater flow regime. The flow can extend this area also. This can also extend this area. All these places it is extended like this. But we are just considering a particular cross sectional area. This is what is, this is at this point is, this is what is would give you that this provides you the change in the, this is the L, this is the L, this is the L del L, this would be this point and this point. You find out this would give you the hydraulic gradient, and this would give you the del H. This will provide you the del H, difference of the water level in the aquifer, difference in the water level in the aquifer, and del L is known, area is known, and the quantity of flow. This is the flow quantity. This is Q. Q is the flow rate. Q is the flow rate, which is known as this, say, meter cube per day or meter cube, say this is meter cube per day, etc. So this is K is known as meter per day. K is this hydraulic conductivity. Hydraulic conductivity in meter per day, and say del H by del L is without coefficient, without without units, and A is the area. This is cross sectional area of the cross section, is given in terms of meter square. So you can find out the Q as is equal to meter cube per day or meter cube per year. That is how the condition is, meter cube per year, meter cube per day on the time rate coefficient, because in many cases the speed is very slow in aquifer, so we generally need not have to represent it in terms of minute or in terms of second, things like that. Mostly if you are representing in terms of day is fair enough, because the velocity is very low. So you can see here this is known as the Darcy's law. But this Darcy's law provides to be somewhat quite simplistic in the sense that there are few things it generally understands here. If you are just observing this flow, right here, you can see this. If this is the direction, you just see if you can see in terms of the change in the hydraulic head. If you just consider this change in the hydraulic head here and the change here, you see this one is del H, this one is del L, isn't it? So this is the 2 points in the aquifer. This is the 2 points in the aquifer. This is del H, this is del L. Okay, is that clear? So having said this particularly is one flow direction. It's not necessary that the flow would be only in this direction. There would be a flow in the normal to this direction of flow as well. The spread of dispersion would be in the case of normal to the direction of this flow. So here you can see this is known as the transverse flow. This is known as the longitudinal flow. This is known as the longitudinal flow. We know it should be essentially depending on several other purposes. But everything said and done, this Darcy's law has proven the test of time and is very much used. Is still very much used in almost all kind of groundwater regime calculations, because it provides a very good quick estimate. And this is Darcy's law. So the weakness, if we can see, weakness of Darcy's law, one is it only discusses flow in one direction, but not in other directions. 2 is hydraulic conductivity K as identified. K is a constant, a site specific constant. K is a site specific constant, which itself has the potential to be called function. has the k is, which is itself as a, can be called as a function. So you can see is what it says is the k here, k at, if you just try to observe this, k at this point, k here and the k here are same. But if you just think of an aquifer, there would be always, as you know, in most of the geologic materials, in the most of the natural materials, the anisotropy is quite common. Disparities are quite common. So you can very well see that this k would not remain constant in all cases. The k would not remain all constant in all cases. Suppose in such cases, in cases like where there is a sudden a block of igneous formations or igneous intrusions coming in, the k is likely to change. This is igneous intrusions coming in, the k is likely to change. So k itself cannot be a constant. To understand k as a constant over a length of aquifer, say about 2 kilometers, 3 kilometers, 4 kilometers, is too simplistic. K itself cannot be a constant. So k can be a function by itself. The nature of the functions can change depending on the construction of the materials in the aquifer, isn't it? So, but then again, weaknesses are this, whatever we say that, this, but this is quite popularly used. As I have said, there is the thing is, so the important change is in another important area of weakness, as I have discussed, is that it only discusses about the flow in a particular direction, but it does not discuss about the dispersion. That is how it is taking place, dispersion taking place all around the aquifer. But then again, as you can just observe, in a aquifer flow like this, we can also compute the Darcy's coefficient across the plane of transport. This is how this is what is the plane where the transport is taking place. Across, this is the plane where transport is taking place. On all these cases, the water is moving like this. We can also compute the value or across the plane can be computed. This is what we generally try to do in the dispersion model. But the dispersion model, we will just briefly discuss about the dispersion model. But here again, this is what is the weakness of this Darcy's law. But the simply very important thing is in the strength is, if you just, why Darcy's law is so popularly used, it is popular, it provides a good, it is popular because it provides a good fast estimate, Suppose in case you do not have data, or you do not have anything to bank on, in such cases the fast value is important value. Say suppose in a test, if you are doing a titration test or anything like that, if you just know that, okay, this is be the value, this is the one value on which I can say the ultimate value, the most correct acceptable value, the most acceptable value would be close to. The most acceptable value would be very close to this value. It gives a good first estimate. In any engineering design or any engineering decision making, the good first estimate is a very important thing, which must have to have a good first estimate. That when you are designing anything and any installation, we are discussing about, say, what is the life of the installation. We generally have an estimate, but it's not necessarily that installation would live up to that years, or it might give the time may be reduced, time may be increased, but a first estimate is an important thing. And this Darcy's law provides a good first estimate. This number is another important thing about Darcy's law is it is generally considered that in a period of time the flow condition steadies to obtain a steady state flow, to obtain a steady state flow, particularly in areas of low rainfall and uniform pumping, particularly in areas of low rainfall and uniform pumping, where is the pumping groundwater is being pumped uniformly and there is a low rainfall. In such cases we can consider that this Darcy's law works well. This is a strength, it works well in such situation. Okay. Another important thing is that there are some approximate values that we will discuss about. Approximate values of this hydraulic conductivity. Material is clay, the conductivity is this one is not so important, but this one is important. Ground per day per feet square, say gallon per day per feet square, so meter per day, whereas this is 0.01. I think this one is more important value, 0.004. Clay is like this, sand, we can find the value of sand to be like this, sand, gravel would be gravel and sand is 400, and sandstone is about 4. Limestone, you can put limestone also. Limestone is about 0.04. Limestone is about 0.04. Okay, these are the values. So these are the values for approximate values of conductivity. So we can find out, we have found out porosity, we have found out the specific yield, we have found out conductivity. Next, in the next class, I'll discuss about the other aspects of groundwater flow. All right, 5 minutes break. Well, we begin the discussion again. We are starting with this, we have discussing the groundwater flow. Then the flow velocity is the thing that that we will discuss now. Flow velocity. Flow velocity. Having to see in the flow velocity part, let me explain few things about here. What is generally, if you can see that generally a very popular notion that Q is equal to A into V, that A is the area of the cross section, V is the velocity, that so also V is equal to Q divided by A. Here in this Darcy's case, if you Q divided by A is, as we have done for this versus this Ka dH by dl that we have done for Q, if we this the K cancels out, K dH by dl. That is, this very simply can be written like this, velocity as this. So this velocity is known as the Darcy velocity. Darcy velocity. This requires a certain explanation here. Darcy velocity. This Darcy velocity, if this can be, this is known as the Darcy velocity. Now let me explain this Darcy velocity here. Suppose in this case, so here, say in case of a Darcy velocity, what is generally understood is this. This is, if this is the cross section of the aquifer under consideration. It talks about that their cross section, there will be some impervious zones, some pervious zones like this. Say here, not coming in there. Coming, now it's coming. Okay, so here you can see this is the impervious section. If you just make a section in the aquifer, this is a section. The section of the aquifer. These are the impervious zones, impervious sections or impervious zones, you can write, or sections. Here this is the area, the white portion is the void. This is the void. People generally do not use them. So even if so, that is the beauty of this Darcy's law and things like that is, you can have a very quick, fast estimate. 5 years. It would take 5 years. So whatever things you want to do, you have to think about the changes within that time. So here, but well, I mean, having said that, this is one is a 5 years and things like that. So here again, as we have said, it has mostly discussed about the flow, but this Darcy's law does not discuss about the dispersion. Let me briefly put light on what is with the dispersion and things like that. So this has there are 3 assumptions to make here. Any case in 1, 2 and 3. 3 assumptions here is that ignore dispersion, I'll just take it out, ignore diffusion,
So if dispersion or diffusion is not so good, then after also 10 to 12 years, it will affect.
Yes, it would suddenly, is going to affect suddenly. Ignore dispersion or diffusion of the transported material. Let me explain this. This is ignore dispersion or diffusion. This Darcy's law generally do not take clear care of this. Another is the the polluted substance travels at the same speed that of groundwater, This also is perfectly mixed. When you consider it's perfectly mixed, then you can consider that this polluted substance travels at the same speed as that of the groundwater. And the third is that there is no pumping effect of pumping in between. there is no effect of pumping in between. So, in between the two holes under consideration, in between the two points that we are discussing. So, this is the Darcy's laws, the typical assumptions of Darcy's law ingrained with the inefficiency by which the Darcy's law cannot estimate several other things. But let me just briefly discuss about what is the important difference here is that here along the head, along the decrease in head. So, it is essentially discussing about mostly the transverse flow. But transverse flow, sometimes this longitudinal flow and transverse flow, this longitudinal flow sometimes is more than transverse flow. Transverse flow. So, what is observed here is instead of the plume might look like this, the transverse movement has been much more than the longitudinal movement has become much more than the transverse flow. It is quite possible, in most cases it is quite possible that this kind of situation can take place. So, in such cases you can see that in that cases it is not quite possible to explain the flow, total flow by means of Darcy's law. We have to find out another parametric coefficient, parametric functions to deal with this kind of situation. So, instead of movement in the x direction, we will have to consider the movement in around y direction. So, this kind of thing, this is possible with the differential equations that we will not deal with, but I will just tell that there is a scope of use of those kind of methods to deal with situations like this. So, anyway, nonetheless, this is what is generally it would look like, it is how it would look. It will consider this case, it will be like this. So, but one thing interesting here is you must observe here as that this particular, this one, if you just say this one is x, the direction x, the y1 or y1 here, or both sides, this y2,